Okay, Warriors, today what we're going to be looking at is how to graph the relationship between distance and redshift. And so today we're looking at what a computer would see instead of a spectrograph. We saw those dark backgrounds with kind of bright colored lines. We've been looking at those same images in inverse with a rainbow background and dark colored lines. But what would a computer see? Because we had to argue about colors. A computer doesn't. So this is what a spectrograph looks like if it is generated by a computer. And so you'll notice this side says relative intensity. So it looks at the brightness of those different lines that we saw. And remember that each individual atom has a different set of jumps it can make, right? That its electrons can make. And each electron has a different set of jumps it can make. So we're specifically looking at the hydrogen alpha electron. We're looking at one specific electron and where its brightest line normally appears. And so that is this control marker. This, when we look at it in a lab, is where that hydrogen alpha electron likes to go, the shell, the jump it likes to make. And so when we're reading one of these graphs, we are trying to find the peak that would correspond with that control. But it's not going to show up there because these galaxies, there's your galaxy name, they're on motion. In college, when you do this lab, they're going to teach you to read it from left to right, and you're looking for the middle of the three peaks. But the first peak is kind of rude, and so I always read them from right to left because I found I get more success. And so what you have over here is noise. When we look through our galaxy, we see some of these bumps and lines appear. And so this is kind of the Milky Way, this double bump right here. It's kind of a friendly bump. It always says, hi, how are ya? And so you go noise, 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 1, 2. You're always looking for this one. A lot of times this is going to be the tallest peak. In this case, it happens to not be. You're going to take and you're going to draw a straight line down into that x-axis. And then what we're looking for is how far away is this line that we drew from this control line. So on this one, what we see is each one of these tick marks is about 10 angstroms. So angstroms is our unit. I don't care that you know what one of those is, but just know that each line's worth about 10. And this is real life. These are real galaxies, so it's not pretty. It's not perfect. So our H sub alpha line isn't quite on that tick mark. So you're going to have to estimate as a scientist. Make sure that whatever rule you use, you stick with consistently in terms of your estimation, because you are going to have to make estimations. So if we say that's about 10, 20, and is that enough with that little bit to call it 30? We decided it was, so this one would be 30 angstroms. So this is what I would record. Now, I did pick a random set of data, so I'm going to choose another one here. And so how would I read this graph? So in my graph, you'll notice there's a spot that says distance. Your distance is given at the top of your data point. That's right here. So I would have to put 30 million light years in for my distance. And then it's going to ask me for my redshift. So again, I'm reading on from right to left, noise, noise, noise. There's the Milky Way wave and hello. I go to that second bump, 1, 2. This time the first bump was nice. I'm going to take a line and I'm just going to snap it straight. And now I'm going to count how many tick marks it is from here to here. So this one I would say is about 10, 20 angstroms. So my distance here is going to be, or my redshift here is going to be 20 angstroms. So that's the other number I need for my graph. So as you go to place these into your graph, that is the two numbers that you're going to need. So this is my redshift. And then my distance is right here. All right.